Lost in the fog of a cosmic storm, floating on whimsical wavelengths is the norm. Dancing through the stars, chasing spectrums of light, riding the waves that are just out of sight.
Whimsical Wavelengths is here again. Today we're going nuclear. And I was going to start with a nuclear joke, but I think on second thought it would be too radioactive. Yes, today we're going to explore what we thought would have already happened, but is likely about to happen in the cosmos above our heads. An event that may not have super in front of it, but it's still large, bright, and fascinating. A nova. But first, just to address some of the feedback I got for doing the Dante's Peak episodes. And I'm still going through some of it. We'll think a bit more about how to do any movie-themed episodes in the future. Clearly, I didn't go quite as into detail in the primer as perhaps I should have. You gotta remember, this is a learning process for me too. But this time, we're talking about novae. Novas? Not sure, and we'll get to that question too, what the plural is. In putting together this episode about novas, I started going down a rabbit hole of wondering how many terms need to be defined before we get to the exciting stuff. Stars undergoing nuclear explosions. Well, the simple synopsis is 3,000 light years away from Earth, a white dwarf star named T Coronae Borealis, known to astronomers simply as TCRB, is about to have a brief but powerful runaway nuclear reaction. The nuclear reaction will cause it to go from not visible in the night sky to visible by the naked eye. No telescope required to see this explosion. That begs the question, why did the star go to therapy? Because it was feeling like it was about to have a supernova collapse. To help me and the rest of us break it down, I pulled a family favor. As a young budding scientist, I had one person in the family that was into science, my uncle. I think it's fair to say he did not take the standard path, or I'm about to get an earful. So a miniature rundown of Dr. David Zurek's bio, who'll be joining us in just a moment. Graduated in 1990 with a bachelor's in physics and astrophysics. The same year, the Hubble Telescope was launched. Sometimes timing is everything. Now he works at the American Museum of Natural History, where he spends 50% of his time doing independent research and 50% dealing with IT for other researchers at the institution. So over the last 20 years, Dr. David Zurek had worked at the American Museum of Natural History in New York, got his PhD in 2018 in astrophysics. And we'll get to it in just a moment. We'll get into more background about him and the Hubble telescope. But let's just step right in, shall we? So you would think, being family, I would know so much more, especially having gone through the academic grind myself. But
you went to my school, as a matter of fact.
I did go to your school. I haven't even introduced you yet, and you're stepping in. This is fantastic. I learned so much trying to follow your academic trail. From papers and theses, from graduate committees, and being a co-author on papers in the prestigious Journal of Nature. And so welcome everyone to my uncle, Dr. David Zurek. And I think there's still a lot more that I don't know, so let's just begin.
Sure. What do you want to know?
Well, I think it's great that I have you here trapped to ask all the questions that I wasn't able to as a kid, especially given that I was really science-oriented. Okay, I'm kidding, mostly. But I did want to begin a bit broad and then narrow in on the topic of novas or novae. So is it like a potato or potato thing? What is the actual plural of the name?
I think because it's Latin, nova comes from Latin, and I think officially it should be novae. I think novas is a acquiescence or whatever, it's more of a colloquial thing, or public, like maybe the public will know what that means more than novae sort of thing. Yeah, so novae is officially the plural. And it's also true for nebulae as well. So there's nebula, nebulae. So they both, it's an AE at the end instead of an S sort of thing. So
Okay. Well, we've got the most important question out of the way now. Personally, I really want to start with the Hubble telescope. So
okay.
much has come from that one telescope. I would argue it's could be the single most important scientific equipment in the 20th century. And I know growing up that you worked on the images from it and primarily looked at Novae. Am I missing anything? Because that's really all I knew.
So well, I worked there from '94 to 2000 at the Space Telescope Science Institute, which runs the Hubble Space Telescope. They also run the James Webb Space Telescope, um, the infrared, bigger infrared telescope that's up in space now too. Uh, but yeah, I would say Hubble. After it was fixed in December of '93, they did a servicing mission that fixed its astigmatism, which
Is that what they actually called it? Astigmatism?
well, its primary mirror was out of spec by a very small amount, which is the equivalent of what we would have as a human as an astigmatism. So
Oh,
we
okay.
had to put glasses on it in order to fix it, basically. And they replaced the primary camera, which was WIFPIC, which stands for Wide Field Planetary Camera. They replaced that with WIFPIC 2, and the WIFPIC 2 actually had the optics in it. And then they also added, they replaced a fast counting detector with a non-instrument that was called CoStar, which was the glasses for the rest of the instruments on the telescope. And so with WIFPIC 2, once we were able to start like imaging properly and with the full resolution of the telescope, we were able to determine ages of globular clusters, for example, be able to resolve all the galaxies in our local group. One of the first things that I was brought on to work on was a recurrent nova called T Pyxidus, and Mike Shara got a proposal through in '94 that where we imaged T Pyxidus to we predicted it would erupt, kind of like we're predicting this present one, because T Pyx was supposed to erupt every 30-ish years, and it was overdue. So Mike wanted to have a pre-eruption image and look at the nebula and stuff like that around it. And we did that, and I did the analysis of those images and narrowband filters. So we took a narrowband filter is basically you're looking at like a very small wavelength region, right around, say, hydrogen, the hydrogen line.
In the visual spectrum, right?
Right. So the hydrogen line, the nitrogen 2 line, oxygen line, sort of thing in the spectrum, and you're looking just around that, and you're sort of imaging that. But then you also take a broadband image too, just to get what's called continuum. So, but nebula only emit in narrow bands, and so this is what I was doing. I analyzed that data, and it tells you a fair bit about the density of the gas, the temperature of the gas, what's going on in the gas, like turbulence wise and things like that. And so we did so that was one of the first papers I was ever on with Hubble Space Telescope data back in '94, '95, something like that.
Cool.
And there was a press release for it, all that kind of stuff too, but whatever. And T-Pix eventually did go off, but I think it went off in 2010. So it was well after it was predicted to go off.
So that was almost 20 years, I guess.
Almost
15.
20 years, yeah.
Yeah.
And we looked at it when it outburst and everything, like seeing light echoes as the light went out and hit the shell around it. The shell would light up, would fluoresce, and so we would image that shell as it fluoresced and then faded away, sort of.
Cool.
Yeah.
I assume that they're doing similar studies right now.
I would hope so. I hope so.
Which means a
We
lot of
did
citations for you too, I would imagine.
we did put in a proposal to do it for this one, but the 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 TAC, or the Telescope Allocation Committee, uh, turned us down. That doesn't mean we can't get the telescope time to do it. It just means we would have to go through a different route. That's all.
I see.
Yeah.
Has Hubble changed how it's been used between when you first started working with it and today? Like, is it changed its mission, so to speak, or how it's used to probe the cosmos?
Well, it's gotten better in some ways because its last servicing mission, which was what, 10 years ago thereabouts, just before, like, when the shuttles were retired. So just before the shuttles were retired, they did one last servicing mission, and they replaced that WIFPIC 2 camera with WIFC 3, which is wide field camera 3, and it has a optical band and an infrared and a near infrared band on it. It's very sensitive. And in the meantime, too, from that first servicing mission of '93, they had they had three additional servicing missions where they replaced one of the other cameras with the advanced camera for surveys, which actually has 3 detectors in it, and they replaced one of the spectrographs with a space telescope imaging spectrograph, which can do everything from the far ultraviolet all the way down to, let's call it near infrared. Can't really go into the infrared. And then in the last servicing mission, they added COS, which is the Cosmic Origins spectrograph, which is just an ultraviolet spectrograph. Though that spectrograph is designed to look at hot stars, nearby star-forming galaxies, and things like that, and to correspond to what you can see at high redshift that has been shifted into the optical band. So we want to look at the rest frame wavelengths of what we're looking at high redshift, but at low redshift. You see what I mean?
Yeah,
So
I got 2 questions, but quickly, what do you mean by
yeah,
rest frame?
so our rest frame is like what we are. So it's not moving, say, and nearby things are maybe only shifted a little bit. Yeah, so things are usually shifted to the red, and that's because the expansion of the universe. You go to very high redshift, and the things that you see in the optical are actually shifted all the way from the far ultraviolet into the optical. And so you want to understand what you're looking at these when you're looking at these high redshift objects. And so you want to look at nearby ones where you can actually study them in much more detail, and you want to look at them in the ultraviolet because that is what has been shifted to the optical for those high redshift ones. And so by rest frame, I mean, like, shifting. We're looking at the wavelength frame, or the time frame of the objects that we're looking at in the sky. So it's
So you could say you're reversing the Doppler shift kind of thing?
effectively, you're making some assumptions about the things that you're looking at nearby are similar to the objects that are really far away.
Yeah,
It's probably a fair assumption, but it's still an assumption.
for sure. We're always making assumptions when we're building physical models of
Exactly,
processes. Like
exactly.
it's but what about the future of the Hubble Space Telescope? With all these SpaceX and Blue Origin, do you think there might be a way to get up there and perhaps fix the gyros and maybe get it to live even longer? Or is this pretty much we're going to keep going until the gyros fail? And the gyros are something that
Uh,
allow the telescope to turn and focus on a particular object.
yeah, the gyros actually keep it at a location,
Yeah.
basically. Yeah, it's also stability and that sort of thing. So image quality is set by the gyros as well. Um, I doubt we will have another servicing mission of any sort to the Hubble. I think they might explore a servicing mission to James Webb when the time comes, because it's a far more expensive thing, but it's actually much further away in the sense of where it's orbiting. But the Hubble is a low Earth orbit, and you would need, I don't know, there's too many things that you would need to replace. I think it's more cost effective to just do other missions. Like there's going to be another mission coming up soon called Roman, which is using some spare mirrors that the military had that they didn't want anymore because they were obsolete as far as the military was concerned, and they gave them to NASA. And so one of those mirrors, which is exactly the same size as the Hubble Space Telescope, by the way, has been made into a new space telescope that's going to be launched in the next 3 or 4 years called Roman, and it's going to be a large area field of view and at the same spatial resolution as the Hubble Space Telescope over that full field of view. And so it's just going to be spectacular. It for the optical and near infrared, Roman will be better than Hubble. So Hubble gives you some spectra and things like that we don't have other things for, and you don't have far ultraviolet for anything else. So I mean, Hubble will be missed, but hopefully it won't be a lifetime before we relook into those wavelengths. So because and there's also budget cuts coming. So I know, for example, Hubble has, I think, a 10% budget cut this coming year and a 20% budget cut the year after, or something like that. So it's like it's not looking good as far as that's concerned. So
it's sad, really. I think, I mean, the public purse is where the vast majority of scientific moving forward actually comes from. So
yeah, I get it. They have a limited budget. They have to pick and choose what they want to support, and that's why every 10-ish years we do what's called a decadal survey, which is surveys the astrophysics community and determines what the priorities of the community are. And so they try, and NASA and the National Science Foundation try to fund things that correspond to that decadal survey. It's not always the case, but it's close.
well, I guess it's time to jump back towards the original topic. And
Sure.
perhaps the best way to go forward, because this is a general podcast, we're not dealing with people that might know more than me.
Sure. Yeah.
So without getting into the weeds too far, perhaps to explain how stars form, because we need a star before we can have a nova.
You need a lot before you have a nova, actually.
Right. I'm just saying we need to start somewhere. So perhaps
Yeah.
talking about star formation, a cloud of gas might be a good place to start.
So, as best we can understand, right now, this is still a pretty hot topic for study. Both simulations and observations is star formation. Basically, we have a cloud of gas, which through gravitational collapse, it collapses down into stars. Those stars are often binaries, so they have a companion star. If we look at the sky in the field, and we look at every star out there in the sky, roughly half of what you're looking at are in binaries. So that means that half the stars you look at in the sky have a companion star with them. The other thing is that that's also where planets are formed too. So planets are always forming around those stars at the same time that the stars are forming. But I mean, I'm not a planet exoplanet person or anything like that. But that is where things happen. And it's important to remember that, like, basically 50% of all the things that you see in the sky are binaries, or at least that they have a companion star, a companion with them. And why is that important? Is because the subject we're talking about today, which is novae, are a binary, and you have to start from a two normal stars, and then let them evolve in time in order to get to what we know as what will become a cataclysmic variable, which is what is nova is. So we can chat about that a little bit more if you'd like.
Sure. Perhaps step out a little bit. I mean, you kind of.
Okay. There's a little bit of jargon there, I get it. But
No. I was more thinking along the lines. I didn't think you used too much jargon at all. It's more like when we first get to the star, it's collapsing under the form of gravity, and eventually
Yep.
that pressure and heat gets to be enough that you can fuse atoms together, which births the star. And then I was hoping to just try to figure out some terms like normal, like main sequence, and how we go from the birth of a star
all
to
right.
what we're worried about, which is a white dwarf in this case.
Sure. So, all right. So when stars collapse, they collapse into, when gas collapses into stars, the stars that it collapses into are in a range of masses. They can range from, say, a tenth of the size of our sun to 100 times the size of our sun. And depending on how massive those stars are, it sets what the result of what the end product.
You mean how
So
they change and evolve? Or
so what they'll end up being, like whether they end up as a white dwarf or whether they end up as a black hole or a neutron star. Those are the three. Well, there's technically four end products, but those are the three that result in something. The fourth end product is no end product, like in the sense that the star completely destroys itself. And that I think it can happen, but it can happen for a very small range of masses, I think. So generally, the more massive a star is, the more likely it will end up as a black hole as the final product. And the reason is because what happens is that when the star forms, the core gets to a certain density and it starts fusing hydrogen into helium, then helium into carbon, carbon into etc. To something else. I don't know exactly what next, but it ends up at iron. And iron, it takes too much energy to fuse beyond iron. So it actually is an energy sink and it starts to collapse. And depending on the mass of the star, it explodes in what's called a supernova. And the result of that supernova is either a black hole remnant or a neutron star remnant. And the black hole remnant is kind of important because that's what we're seeing in the gravitational wave sources from LIGO and stuff like that. So those we know they exist, and we know that they end up in binaries, and we know that they merge because we see gravitational waves from them. I don't want to get into that, but we do know there's plenty of evidence that what we know of as what's called stellar mass black holes exist. We have plenty of evidence that they exist now. We've known that there are supermassive black holes at the center of galaxies for a very long time, but we really don't understand how they formed in the first place. It's unlikely that they formed like a star, so we don't know for sure how they formed in the first place in that sense.
so if I was to make it overly simple, a very large
Yeah.
star near us going into a black hole or a large supernova would kill us. So bigger isn't always better.
That's why people are upset. That's why people freak out about Beetlejuice.
But I thought that was far enough away that that wouldn't.
It's close. It's relatively close.
Oh, you heard it here.
I'm not, but I mean, when it goes supernova, and it will go supernova when it does go off, but I doubt it would like create a extinction event or anything like that, but it would maybe inundate us with a bunch of radiation and things like that. So yeah.
Fun.
Yeah.
So, but we're not waiting for we're not waiting for a supernova, thankfully, not in
No.
this particular
No.
instance. No, we're waiting for a
No.
nova,
Right.
which we didn't really get. I mean, we we danced around it. So fundamentally, if you're a small enough star and you don't go supernova and you don't collapse into a neutron star, you will then form a white dwarf after you've gone through the sequence of fusing different things together. So you get to
Correct.
as high as helium, is that correctly? You start fusing helium, but beyond that, you're no longer able to fuse, and so you collapse down to a
No,
white dwarf?
no. You fuse from helium, and so it depends. But let's say, and basically any star less massive than 10 times our sun, give or take a little bit, will turn into a white dwarf. Anything over 10 times the sun will have a supernova and will either become a neutron star or a black hole. Say, let's take the more massive end of things. And so what's going to happen when it's burning fuel in the core? And astronomers call it burning. It's actually nuclear fusion, but it's just the shorthand for us is to say burning. So we burn hydrogen into helium. Helium is the ash that from hydrogen. Helium then burns into carbon, oxygen, and if you're at the higher mass end, like say 6 or 7 times the size of the sun to 10 times, you then burn into neon. So you get oxygen neon as the result, and that's basically where it ends. And then the outer envelopes of the star puff off the surface, and you end up with a core that's left in the center. And that core, if it's the more massive end of things, is oxygen neon mostly. Or if it's normal, like between one solar, if it started as like the size of the sun to say 5 or 6 times the size of the sun, you end up with a carbon oxygen white dwarf. If you are a star that is basic, or not you, but if it's a star that's evolving to become a white dwarf that's less massive than say 0.5, 0.6 times the size of the sun, so like 50%, 60% of the sun, it would evolve into a helium white dwarf, where helium was the last thing that was formed in the core. However, while there are helium white dwarfs in the universe, they did not form through normal stellar evolution. And the reason why is because a star of around 0.6 times the mass of the sun, the universe is not old enough for that star to have evolved to its end of life yet.
Because the smaller the star, the longer it can keep
Correct.
going. It's like
Correct.
it's burning
It
less
takes a
overall.
lot longer. It's right. It takes a lot longer to burn that hydrogen into helium, and it just sits there and does that for billions and billions and billions of years, sort of thing. So, but like say our sun is basically midlife. So it's been burning hydrogen into helium for the last
4.5 billion
four
years.
and a half, 4.5 billion years, and it probably will burn for about that much longer, and then it will evolve up the red giant branch, so that which means it'll expand out. The outer envelopes of the star will expand out, maybe as far as the Earth. Earth might get swallowed. It'll be about that far, and then it'll lose a bunch of mass. But then it ignites helium in the core at the top, and it's called what's called a helium flash. The flash, it's a sudden ignition of the helium in the core, and then it burns helium for a few 100 million years, because the lifetime of this final stage is not very long in astronomy.
Yeah, I mean, have you ever tried to talk about this to people who know nothing about science? They're just like, "What do you mean 4 billion years? What do you mean 200 million years?"
Well, it's a matter of like, because I do realize that these numbers are huge as far as like the human lifetime is concerned, but in astronomy, the universe is 13.5 billion years old. We're talking, the sun 4.5 billion years old. The lifetime of what we call the helium burning phase of a star the size of our sun is maybe 300 million years. then the time for it to cool from after that, from because what you left at the after that is just the very, very hot core of the star, which is well over 100,000 degrees. And but it has to cool, and it cools relatively quickly. And by quickly, I mean tens, hundreds of thousands of years, maybe, sort of thing. So all of these times are much longer than humans can even really understand. But to me or to other astronomers and astrophysicists, it's just a matter of, it's abstract. You just think about things in with compared to each other. You don't think about things as compared to me or compared to you, sort of thing. So
Right. Okay, so we have this white dwarf. Regardless of how it's created, we have this white dwarf, and
Yep.
it's in one of these situations where 50% of all stars are. It has a companion star.
Correct.
So now we have to go from my understanding is it steals in some way material from its companion star, and then all of a sudden it has enough hydrogen to flare back up and fuse again.
Yes. So it has to be close enough to each other. Like, so the white dwarf has to be close enough to its companion that it falls within what's called the Roche lobe of the companion star. And the Roche lobe is basically the surface at which the gravity or the gravitational potential between the two stars is equal. Does that make sense? So,
Yeah.
so because at that point the material from the companion star, it gets shaped into like sort of a kind of a teardrop-y shape or something like that, where it goes through what's called Lagrange point 1, which is the center of this, because every object has a Roche surface. So there's like it's basically a figure eight, and there's like where the two come together is where that's called the Lagrange point, and the material actually funnels through that point and then spirals down onto the surface of the white dwarf. And so yes, it's stealing surface material from its companion star. That builds up on the surface layer of mostly hydrogen and some helium, obviously, because everything is made of those two for the most part, but it's majority of hydrogen. And once that layer builds up to be thick enough or dense enough, it goes through what's called a thermonuclear runaway, and it just basically a bomb goes off, and the whole surface erupts almost instantaneously and explodes off the surface of the white dwarf. So all the material that accumulates gets exploded off the surface of the white dwarf.
All of it doesn't keep anything.
Pretty much. I mean, my coworker or former boss, Mike Shara, he and his collaborators have models that show you have to be relatively massive white dwarf in order to not lose everything. If you're like a white dwarf, a typical white dwarf in the field we see, which is like, say, white dwarfs that are as massive as 6/10 to 8/10 the mass of the sun, they will lose everything that's accumulated. If it's like a white dwarf that's like 1.2 times the size of the sun, it may accumulate. Actually, it may some of it may stay on the surface, and so the white dwarf may actually grow in mass over time.
Oh, well, and I'm going to jump ahead to a question that I was going to come to and say,
Okay.
well, what I read, because I have to prepare somehow to have this conversation.
Yeah.
1.3 solar masses is about what it needs to happen if that white dwarf were to go through one of these. It would actually explode as a supernova.
So it's
So it is
1.4. It's 1.4. But whatever. But it's yeah, whatever. But yes, and that's this is those type of supernova are called supernova 1As, and they are the type of supernova that are used as standard candles for determining distances in the cosmos.
because you know how big that explosion had to have been because of the
Basically,
size.
basically. You know how luminous it should be, etc., that sort of thing. So yeah,
Right. Cool.
yeah,
So there is a fun fact that you were a co-author in at least one previous paper, and no, I did not read all your papers, that used TCRB, which I'm just going to use its acronym so I don't have to pronounce it multiple times,
yeah.
as a supernova event. And it's happened before. We've recorded observations in 1866 and 1944. So clearly these events can be cyclical, as we've already talked. So perhaps I should frame it a bit more from my own biases and perspective as a geophysicist. We look at earthquakes in somewhat of a similar way, where the plate tectonics are constantly moving. And
Hmm.
we talk about reoccurrence intervals. So we can't predict when an earthquake is going to happen, but we can predict a time frame based on the plate movements and how often these things happen.
Yep.
So I assume something similar goes on for these novae,
So,
except we only have two in this particular instance, right? So how do you go about doing those
oh,
sorts of predictions?
you mean to? Oh, so this particular prediction wasn't done on a timing basis in the sense of like what we did with T-Pix, because with T-Pixidus we had five previous eruptions that we looked at and said the recurrence time is 27 to 30 years, and then that's why we started looking in 94, because that would have been 30 years basically from the previous outburst, and so that's why when it went off another 12, 15 years later, it was basically overdue by 10-ish years, right? So in this instance, what they did was they don't have a lot of data pre-outburst of T Coronae for the first eruption, but they have a lot of data pre-eruption for the second one. And what they see in the light in the light curve, or in its luminosity pre its eruption in 46, you said, or something like that. But
1944 is what I have written
44.
down.
Okay, yeah, 44, fine. But there's a slight dimming of it, and it's once it starts to dim, it's 6 months or 12 or something like that, 12 months after that it went off. So Brad Schaefer, who is the person who came up with the prediction for it to be erupting this summer, he said, well, it's doing the same thing. So if it's gonna do the same thing, it should erupt this in this time frame, and that's why the quoted numbers are what they are, sort of thing. And I think the error bar is obviously wrong that he gave, but that's besides the point, right? But I mean, the thinking was still correct, but it's just that it's a little that maybe his error bar should have been bigger. He should have said, plus or minus a year rather than plus or minus 3 months or whatever it was he gave it.
So you think it's still kind of imminent? It's just a matter of
Oh
when.
yeah, 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 yeah. It's definitely imminent. I think it'll probably go off. It might go off. I mean, it could go off anytime. But I would bet it goes off in the next year. Yeah, yeah.
Okay, so what is actually happening when the light dips or becomes less?
It's a good question. I don't know exactly what's going on. Usually, something like that is because some opacity is what everything has. So like hydrogen has a certain opacity, helium has a certain opacity, etc. But it usually has to do with when things start to get ionized and the light gets absorbed more in those wavelengths, which then reduces the total flux. So, and which means that there's a buildup of energy at some level. Geology analogy would be the buildup of the plates, the tension of the
Stress.
plates underneath each other, right? So like the stress sort of thing, and you could think of it that way. I don't think that's the best analogy, but it's like it works. uh, but yeah, it should certainly erupt. I don't. I mean, the thing is, like, as you were pointing out, that this is this is one of maybe a dozen or so novae that we know recurs. that are called a class unto themselves called recurrent novae. However, it's very likely that every nova recurs. It's
Just
just
at
that it's a
time
matter of
scales.
time scales are much longer, and so therefore, and by longer it's 1,000 years, 10,000 years, who knows, right? Sort of thing.
Yeah.
So, so
Makes total sense. Okay, well, I just have really two more questions, I think,
sure.
unless I have skipped over something that you feel needs to be filled in.
No, well,
Um,
we can always do another one at some point.
yeah.
Yeah.
So two more questions. One, are there any scientific projects or perhaps astronomy type shows in the sky or events that you're looking forward to in the near future?
T Coronae Borealis is certainly an interesting one. But I'm actually looking more forward to the various telescopes things like that are going to be coming online soon. The European Space Agency just launched Euclid, which is a wide field survey telescope. It's nominally going to be looking at gravitational lenses and things like that as its primary science, but it'll be useful for lots of other things. Roman is coming up in a couple of years. The Rubin telescope should be coming online in the next couple of years, and it's going to be doing what's called the Large Synoptic Survey, and it's going to be an all-sky survey for several years, and it's going to be finding, and the quoted numbers that they say that's like 10,000 transients a day is what they predict that they're going to see. Transients are things that pop off that change in brightness every day, and the primary some people's primary science is supernovae, some people's will be novae, some people's will be dwarf novae, or binaries or flare stars, or there's all these sorts of transient phenomena that happen in the sky and on timescales of hours, days, weeks, that are going to be extremely interesting coming, and all of this is coming online. The data, again, the European Space Agency has a mission that's still taking data called Gaia, which is measuring the motion of all the stars in the sky, getting distances, very, very precise distances to all of these objects in the sky using a method called parallax. If you want to know what parallax is, it's basically hold your thumb at the length and blink your eye, and you'll see how your thumb moves, the background moves behind your thumb. That is parallax, except you're using stars and the field of stars behind it to determine the distance, because you can then use geometry to say what the distance to that star is. Yeah, if you're interested in exoplanets, there's the TESS telescope, and I think Plato, which is another European Space Agency mission that's going to be coming online. A lot of these, very interesting stuff. The unfortunate thing is, like, my science has concentrated in the ultraviolet in the last 20 years, and unfortunately, after Hubble Space Telescope, there is no ultraviolet that I could use. Now we'll see. Maybe there'll be a mission. I know there are people that are proposing missions, but by the time those get launched into space, I probably won't be doing much.
Well, that laugh is the perfect segue to the final question.
Yeah.
And the one that I'm going to do for every single guest that ever comes on. What is your favorite science joke or pun?
Oh, oh God, I don't know.
And for the audience, I do try to warn everyone that this question is coming, so they can prepare a joke instead of catching them off guard.
Oh, I don't have one. I didn't prepare one. Sorry.
Really?
No. Yeah, unfortunately, I don't have one right off the top of my head. I've heard some bad ones, but
There's so many bad ones. In fact, we use a lot of them. The top of the
yeah.
show before the interview has started, I used the one, "Why did the star go to therapy?" Because it was feeling like it was about to have a supernova collapse.
Oh, Jesus.
Yeah, I know.
Uh,
I didn't say they had to be good.
there are some. I think some of the funnier things that I've come across are like like titles of some papers and things like that. My boss had a paper back quite a few years ago in the journal Science, and I think the part of the title was Promiscuous Stars, and it had to do with the fact that in a cluster, stars change partners a lot, sort of thing, because they interact with each other and their partners change, so they promiscuous. So.
That's a good one. It's amazing what you can hide as Easter eggs in your own science.
Yeah.
Well, I hope you enjoyed the interview and learned a little bit about novae, especially the proper plural. Well, tune in for 2 weeks from now when we go over the High Altitude Auroral Research Program, or HARP, and dig around a little bit at some of the weird and wacky ideas of how people think that particular set of equipment and research program operates, and hopefully learn something in the process. And this is also where I'll add an addendum, if and when the TCRB ever does undergo that runaway nuclear reaction and creates a nova. Until next time, if you've enjoyed the episode, subscribe. And if you have subscribed already, thank you. Tell a friend. Look in the show notes for a Patreon account where you can help keep this podcast running, as well as a Discord server for those Patreons who just want to ask me more random questions. And if I don't know the answer, I'll do my best to find the answer, or perhaps find someone who could do it as part of an episode in the future. Thank you so much.
Lost in the fog of a cosmic storm, floating on whimsical wavelengths is the norm. Dancing through the stars, chasing spectrums of light, riding the waves that are just out of sight. In a world so chaotic that misbehaves, melodies that echo show us sex always. Colors intertwine, painting the sky. We're lost in the rhythm as the universe flies by. Oh, we're tuned in, feeling the beat of the unknown. Can you hear it? It's echoing through your bones. In this melodic maze we